In this class, we will discuss about vector algebra. Specifically, we will discuss about vector addition, vector subtraction, and vector components. Before starting, I will ask you a couple of questions. How is vector algebra different from scalar algebra? Can you guess why it is different?
Vectors have direction as an extra quantity along with magnitude. I see this as a differentiating factor from scalar algebra.
You are correct. We need to take into consideration the direction along with the magnitude when doing vector algebra. We will now discuss the concept of vector shifting. Consider three vectors as shown. All the three vectors have same magnitude and direction. Thus they specify identical vector quantity, which could be a displacement vector or a force vector. A vector can be shifted without changing its value if its length and direction are not changed. Therefore, the vector shown can be moved to another place if its direction and magnitude are not changed. This is a very important property of vectors which we make use of quite often. We will now discuss the concept of displacement vector. Consider the following three paths taken by three different particles. Even though the paths taken by all the three particles is different, the initial and final positions of the journey are the same. Therefore, the displacement vector, which is the shortest path from initial to final positions, in all the three different cases is the same. Similar to displacement, a displacement vector tells nothing about the actual path taken by the particle. It only represents the overall effect of the motion, not the motion itself. We will now discuss the concept of adding vectors geometrically. Consider a particle which has traveled from point A to point B via one path. The path taken by the particle is not a straight line. The displacement vector of the particle from A to B is a straight line drawn starting from A and ending at B, pointing towards B. After reaching B, it took another path which is again not a straight line, and reached point C. We can represent the displacement vector of the path from B to C using another vector drawn from B pointing C. Also, the overall displacement of the particle starting from A and ending at C is a vector which starts at point A and ends at point C, pointing towards C. The net displacement vector, AC bar, can be represented with two successive displacement vectors, AB bar and BC bar. The net displacement of these two displacements is a single displacement from A to C. We can represent the relation among the three vectors using the vector equation, AC bar is equal to AB bar plus BC bar. With this example, we have also identified a procedure for adding any two-dimensional vectors, AB bar and BC bar, geometrically. On paper, sketch vector AB bar to some convenient scale and at the proper angle. Sketch vector BC bar to the same scale with its tail at the head of the vector AB bar, again at the proper angle. The vector sum AC bar is the vector that extends from the tail of vector AB bar to the head of vector BC bar. This process of vector addition is called tail to tip method. That is, start at the tail of first vector and reach the tip of the last vector. This method of addition can be extended to any number of vectors. While using this process, we make use of the concept of shifting vectors. The second method to add vectors is the parallelogram method. It is fully equivalent to tail-to-tip method. In this method, the two vectors are drawn starting from a common origin, and a parallelogram is constructed using these two vectors as adjacent sides. The resultant is the diagonal drawn from the common origin. We will now take two vectors and use parallelogram method to add them. Consider two vectors v1 bar and v2 bar. Now we need to add these two vectors using parallelogram method. Step 1. Draw the two vectors starting from a common origin. We know that a vector can be shifted if its magnitude and direction are not changed. Using this concept of shifting vectors, we shift vector v2 bar such that its tail coincides with the tail of vector v1 bar. Step 2. Construct a parallelogram using these two vectors as adjacent sides. For this, we draw two lines parallel to the two vectors. Step 3. The diagonal drawn from the common origin is the resultant vector. Draw a vector starting from the common origin to the opposite end of the parallelogram. This is the resultant vector. If we add the same vectors using tail-to-tip method, we get the same result.